In this video, we will make some observations about probabilities. Recall that an event E is a subset of the sample space. Also, note that the number of elements in E can never be less than 0. You can never have a negative number of elements in a set. So 0 is always less than or equal to the number of elements in the set E, which is always less than or equal to the number of elements in the set S, because E is a subset of S. Now if we go through and divide this inequality by the number of elements in the sample space, we get our first observation about probabilities. 0 is less than or equal to the probability of an event occurring, which is less than or equal to 1. So all probabilities are in between 0 and 1. You'll never have a negative probability, and you'll never have a probability greater than 1. Notice that given a set E, which represents an event, given a formula about the cardinality of the set, we were able to convert that into a formula concerning the probability of the event by dividing the formula by the number of elements in the sample space. In general, this is something we can do. For example, we know that the number of elements in the event plus the number of elements outside of the event set equals the total number of elements in the sample space. You can see this by imagining a Venn diagram. If you count up all the elements inside the circle E, and then count up all the elements outside of the circle E, you're going to get the total number of elements in the box. Now, just as we did before, we can divide both sides of this equation by the number of elements in the sample space. And this gives us another observation about probabilities. The probability of an event occurring plus the probability that the event does not occur equals 1. And this makes sense. Consider the probability of looking outside and seeing whether or not it's raining. If the probability that it's raining is 40%, then it makes sense that the probability it is not raining must be 60%, for a total of 100%. Recall we had a formula which gave us the cardinal number of a union. What it told us was that we could find the number of elements in the union of two sets by counting up the number of elements in one of the sets plus the number of elements in the other set, and then subtracting off the number of elements that are in both sets because they were double counted. If we go through and divide this formula by the number of elements in the sample space, we get another formula concerning the probability of an event. In this case, it says the probability of the union of two events can be found by finding the probability of the first event plus the probability of the second event and subtracting off the probability that both events occur. Now we're going to look at how we can use Venn diagrams with probability. We'll do this by considering an example. Suppose a company makes LED flashlights, and when they make these flashlights, two errors can occur. One, the LEDs can be defective, and two, the batteries can be defective. So we'll let L represent the first event, the event that the LEDs are defective, and B represent the event that the batteries are defective. Now suppose as these flashlights are coming off the assembly line, one person simply tries to turn one on. And if it doesn't work, they put the bad flashlight into a pile and record how often this has happened. And suppose that in doing so they find that 10% of the flashlights have some kind of defect. So what they've just discovered is that the probability that either the LEDs are bad or the batteries are bad. This is 0.10, or 10%. Now suppose that someone goes to this pile of bad flashlights and removes all of the LEDs. And they find that of the total number of flashlights produced, including the defective and non-defective flashlights, that 6% have bad LEDs. So what they just found was that the probability that a flashlight on the assembly line will have a bad LED is 0.06. And suppose that another person goes through and tests all the batteries and finds that of all the flashlights produced, the probability that they have a defective battery is 0.07. Then we'd like to be able to answer some questions concerning these flashlights other than the information already given to us. For example, what's the probability that a flashlight does not have a bad LED and does not have a bad battery? In other words, it works perfectly well. What's the probability that it has both problems? So both things would need to be fixed. Or what's the probability that it has a bad LED but does not have a bad battery? Or another question might be, what's the probability that it does not have a bad LED but it does have a bad battery? So these are all questions we may want to answer, but we don't immediately have the answers for. Let's begin by filling in the Venn diagram. Before, we used Venn diagrams to hold cardinal number information. Well, it makes sense that we can also hold probability information in Venn diagrams, the same way that we can convert a cardinal number formula into a probability formula. Now, one thing we know about a probability Venn diagram is we know the size of the sample space. Everything inside S has to equal 1. There are two ways to see that this is true. One is to simply figure out what the probability of S is, and two is to think about what the probability of S means. The probability of S is the probability that something in the sample space occurs. Well, that probability should be 1 because it's guaranteed that something in the sample space will occur. But you can also do it by simply writing down the probability that something in the sample space occurs. It equals 1. Now let's see what information we have. We know the probability of the union, but that's a rather large space. We know the probability of L, but that takes up 2 regions. And finally, we know the probability of B, but that also takes up 2 regions. So we can't immediately write any of these down. Just like we did with the Venn diagrams using cardinal numbers, we're going to need to use some formulas to help us here, and the formula we're going to use is the probability of a union. We know that the probability of L union B can be found by taking the probability of L plus the probability of B minus the probability of L intersect B, or L and B occurring at the same time. Writing down the information we have, we know that this is 0.10 equals 0.06 plus 0.07 minus the probability of L and B. And if we solve, we see that the probability of L and B equals 0.13 minus 0.10, which is equal to 0.03. So we know the intersection is 0.03. In fact, that answers one of our questions. The probability that a flashlight will have both defects is 0.03, or a 3% chance. Next, we know the total in L is 0.06. So if we've already used up 0.03, the missing piece is 0.03. Likewise, we know the total in B is 0.07. So if we've already used up 0.03, the missing piece is 0.04. And finally, we know that the total in S is 1. And if we've already used up 0.1, that leaves us with 0.9 outside of S. So now we can fill in the rest of these probabilities. The probability of L complement intersect B complement. So they do not have bad LEDs and they do not have bad light bulbs. That's 0.9, or a 90% chance that there's no defects. The probability that they have a bad LED and their batteries are not bad, well, that's 0.03. And finally, the probability that their batteries are bad, but their LEDs are not bad, it's 0.04.